Hello everyone. Today we'll be studying logic gates. Actually, the term logic is applied to digital circuits used to implement logic functions. Several kinds of digital logic circuits are the basic elements that form the building block for such complex digital systems as the computer. The lines connected to each symbol are the input and output. The inputs are the left of each symbol and the output is on the right side. The circuit that perform a specific logic operations AND gate or OR gate is also called a logic gate. What is the inverter? The inverter or the NOT gate perform basically the inverse function. That's why it's called inverter. Perform the operation called inversion or the complementation. The NOT operation changes one logic level to the opposite logical level when the input is low, the output is high, and when the output is high, the input is low. The inverter changes one logic level to the opposite level in terms of it changes from 1 to 0 and 0 to 1. The truth table for the inverter or the NOT gate is if the output is given as 0, the input will be 1 and vice versa. When the high level is applied to an inverter output, a low level will apply on its output. When a low level is applied to its input, a high level will be applied to its output. The logical expression is represented as this complement function. This is the logical symbol. This is the logic. This is the sign of the NOT gate. And this is a NOT gate. And this is also a NOT gate. And now AND gate. The AND gate can have two or more inputs and perform what is known as multiplication. The output of AND gate is high when all the inputs are high, otherwise all the outputs are low. The output of AND gate is high when all the inputs are high, otherwise all the outputs are low. And these are the operation of AND gate. An AND gate produces a high output only when all the inputs are high. When any of the input is low, the output is low. Therefore, the basic purpose of AND gate is to determine when certain conditions are simultaneously true as indicated by high level on all its inputs and proceeds a high on its output. This is the logical symbol and this is the truth table. In this is A is 0 and B is 0. Both the inputs are low. The output will be low. In this, one input is high and one input is low and the output is low. In this, one input is low and one is high, the output is low. When the condition is when both the inputs are high, then only your output will be high. This is the symbol. This is the logical expression. It's a logical expression saying x is equal to A and B. So you will apply a logic gate and this is the logic gate and this is x is equal to A into B is the representation. These are the three inputs and this is also a representation of the logic gate. For 3 input AND gate is if you are having a 3 input AND gate, then this will be the truth table. X is 0, Y is 0 and Z will be 0. When all the inputs are high, then only your output is high. Otherwise, in any of the cases, whenever a few inputs are low, the output will definitely be low. Now, 3 input gate using 2-1 AND gates. So this is also a symbol. To determine the total number of possible combination of binary input to a gate is determined by the following formula. n is equal to 2 to the power n, where n is the number of possible input combination and small n is the number of input variable. For example, two input variable, if n is equal to 2 to the power 2, then there are 4 combinations. When there are 2 to the power 3, then there are 8 combinations. 2 to the power 4, then there are 16 combinations. And now we will study OR gate. OR gate can have two or more inputs and perform what is known as logical addition. The output of OR gate is low when all the inputs are low, otherwise it is always high. So this is basically a reverse condition of AND gate. When any of the input is high, you will get a high. Otherwise, you will get if all the inputs are low, then you will get a low value in the output. An OR gate produces a high or the output when any of the inputs is high. The output is low only when all the inputs are low. Therefore, an OR gate determines when one or more of its input are high and produces a high on the output. You can see the logical symbol, and this is the truth table. Now, next topic. This is the symbol. These are the logical expression. If the expression says that x is equal to a plus b, then you have to perform this. X is equal to a plus b plus c. And if this is the case of 3 input, you will be representing that like this. There are 3 input gates. And what is the NAND gate? Now, let's see what is a NAND gate. The NAND gate is the one of the popular logic elements because it can be used as a universal gate. It is also called as a universal gate, that is, NAND gate can be used in combination to perform the AND or an inverter operation. NAND gate is constructed by attaching a NOT gate and the output at the output of AND gate, and that is why it is known as a NAND gate. Okay, and it is also called a NOT AND gate. NAND gate has 2 or more input and only one output. The output of NAND gate is low when all the inputs are high. Otherwise, all the outputs are high here. The operation of NAND gate is a NAND gate produces a low output only when all the inputs are high. When any of the input is low, the output will definitely be a high value. You can see this in the truth table. This is the symbol. Logical expression of a NAND gate. It is basically a gate like the NAND gate. NOR gate is also useful. It is a very logical element because it can also be used as a universal gate. NOR gate can be used in the combination to perform the AND or AND invert operation. NOR gate is the combination of NOT gate at the input at the output of OR gate. Hence, NOR gate is the type of NOT OR gate. NOR gate has 2 or more input and only one output. The output of NOR gate is high when all the inputs are low, otherwise the output is low. This is the operation of NOT gate. Basically, you have an OR gate and it is connected with a NOT sign. So this is the basic sign. This is the expression. Basically, you are performing x is equal to a plus b ka complement. So whatever is the result of a plus b or OR gate, you just have to complement that expression and you get the result. If there are 3 inputs, then this will be your gate. Now, this is very important. What is exclusive OR gate? Or it is also called XOR gate. The exclusive OR gate has a graphical symbol similar to mostly like a OR gate, except for the additional curved line on the input side. It can take only 2 inputs. We can't exclude X or gate using 3 or more inputs like we have done in the other gates. If both the inputs are low or both the inputs are high, then it will produce output as low or 0. Otherwise, in any of the cases, the output is also always high. So this is the truth table of for this. Whatever you are applying, you have to just see if both the inputs are same, then you'll get a both the inputs are means 0, then you'll get a 0. Otherwise, any of the input is 1, then you'll get a 1 and same. The logical expression is this. This is how you represent a XOR gate. And in the same way, we have a XNOR gate. The exclusive NOR gate is the complement of the exclusive OR gate, as the indicates by a small circle on the output of the edge of the plus sign. It can only take two inputs, as I have already told you. We can't exclude XOR gate using three or more inputs. If both the inputs are low or both the inputs are high, then it produces the output high or 1. Otherwise, it produces the K map. It is also called Carnot map. The graphical display of the fundamental products in a truth table. Instead of using Boolean algebra simplification technique, you can transfer logic value from a Boolean statement or a truth table into a K map. The map method provides simple procedure for minimizing the Boolean function. The map method was first proposed by E.W. Witch in 1952, also known as Witch diagram. In 1953, it is proposed and it is also called K-map. Construction of K-map. The K-map is a pictorial representation of a truth table made up of a square. Each square represents a minterm or a maxterm. A K-map for n values is made up of 2n square, single variable K-map. The map consists of two squares 2 to the power n square. 2 to the power 1 is equal to 2 square. 2 variable K-map. The map consists of 4 square 2 to the power n square. 2 to the power 2 is equal to 4 square. 3 variable K-map. The map consists of 8 squares 2 to the power n square. 2 to the power 3 is equal to 8 square. 4 variable K-map, that is 2 to the power n square 2 to the power 4 is equal to 16. So this is the example of a K-map. K-map are often used to simplify the logical problems with 2, 3 or 4 cells. Cell is 2 to the power n, where n is the number of variables. For the case of two variables, we form a map consisting of 2 to the power 2 is equal to 4 cell as shown in the figure. This is the max term and this is the min term. 0, 1, this is a plus b, a complement plus b, c. This is 0, this is 0, a and b. Here b is 0 and a is 1, a complement plus b. Here b is 1, that's why it's complement, and a is 0, that's why a. In the same way, this is 0, 0, this is 1, 0, this is 0, 1, this is 1, 1. This is represented by 0, 2 and 1 and 3. In the same way, this is min term and this is max term. 3 variable K-map. 2 to the power 3 is equal to 8. First of all, you have to write down single term C here and AB here. This will be 0, this will be 1, this will be 0, 0, 0, 1, 1, 1 and 1, 0. This is 0, this is 1, this is 2, 3, 4, 5 and 6 and 7. Just consider it, if you fold it, it will go like this. Just remember the numbers. 0, 1, 2, 3, then 4 and 5, 6 and 7. 4 variable K-map. The important part is 2 variable will come here, 2 will come here, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Just see the numbering. This is 0, 1, this is 2, this is 3, this is 4, 5, this is 6, this is 7, this is 8, 9, this is 10, this is 11, this is 12, 13, this is 14 and this is 15. So these cell numbering is very important. The K-map is completed by entering a 0 or 1 in each of the corresponding cells. Within the map, adjustment cell contain 1 complement or 0 are grouped together in 2s, 4s and 8. This is the digital logic gates and or invert and buffer, and these are the truth table. These are the logic gate, and there is a small circle like thing in the front of this panel, and this is a NAND gate, this is the NOR gate, this is the XOR gate, this is the XNOR gate. Just go through the truth table, it's very important. This is a circuit. NAND gate is also called a universal gate. To prove that any Boolean function can be implemented using only NAND gate, we will show that the AND, OR and NOT operator can be performed or derived using only these gates. All NAND input pin connected to the input signal A gives an output A. See how? Then this is working as a, yeah, see, this is the A, this is NAND, this is the complement, this is the complement, this is similar as a AND. One NAND input pin is connected to the input signal A, while all the other input pins are connected to the logic 1. The output will be A. See? Implementing AND using only NAND gate. An NAND gate can be replaced by a an AND gate can be replaced by a NAND gate as the following figure. Implementing or gate, you can implement an AND gate using a NAND gate, you can implement a OR gate using a NAND gate. Just learn how the circuit is working. NAND gate is a universal gate. To prove that the Boolean function can be implemented using only NOR gate, we will show that the AND or NOT operator can be performed using these two gates. The same way, you have to see these logic gates. Multiple input. Extension of multiple input. A gate can be extended to more than two inputs if its binary operation is commutative and associative, and or are commutative and associative, or is x plus y is equal to y plus x. In the similar way, and is x y is equal to y x. Multiple inputs. So these are the expression, and we have created the circuit for the given expression. Multiple inputs. See, now we have three input. This is x, y and z. X plus y plus z, and this is not, and that's why this is the complement. This is x, y, z complement. Just write it down. The XOR gates are commutative and associative. XNOR is an odd function. It is equal to 1 if the input variable have an odd number of ones complement. Just go through this table and see the diagram. The positive and negative logic gate. The positive and negative logic. Two signals value, two logical value. Positive high is equal to 1, low is equal to 0. Negative high is equal to 0, low is equal to 1. Represented by this logic used. Positive and negative logic. Digital gate. Thank you.